Hello, everyone. This is lecture 14 of PTRE 465-531, Petroleum and Reservoir Geomechanics. We will carry on with Module 2 today. We have been able to slow down since we moved the homework, the exam, to next Friday, not this Friday, but the next. And the homework, we moved it from tomorrow, the deadline, to this Friday. It might be a little bit too further that I moved it, but it's okay. It's gonna be it's a semester that started late, so it will finish late. And I know that module 2, from feedback that I received last year, it was the worst for the students. And actually it was hard for me when I was taking the class. So I kind of want to be able to go slower and emphasize some matters of this. The other problem is that the exam is now on a Friday. Well, it was on a Friday. Normally, I didn't have exams on Friday. The problem is that for the exams, I give 24 hours, and so it will roll into Saturday. Somebody can take the exam on a Saturday, basically. And there may be some issues, but I did receive some emails, and I will try to see if I can make some exceptions with the ladies in the office. I believe we can. If we can, we will do it. But yeah, it's a little bit of especially if we are using a testing center, it's a little bit, we are down to their rules as well. So let's see what we can do. I will do whatever I can from my part. And I don't know, I think the next exam is also set for a Friday. I will see what I can do with that. It just happened that I never had an exam on a Friday before. And anyway. So last time we finished going to a point where we were looking at a where is it? Where is it? No. We were here. And I told you how we got these equations. We basically did solve this problem. It was, let me draw on the screen. It's like a semisphere. Where is the pen? So imagine a semisphere, gigantic radius, okay? So any radius, any increases in the X or Y direction basically generates strains that are equal to 0, okay? So any increase you make in the X and Y direction, which is on the cross-section of that hemisphere, is basically infinitesimal. So effectively, my strain is 0. And then I only have strain in the Z direction, okay? So using this idea, I went back into my matrix for linear elasticity, the Voigt matrix. And basically, and I did it very fast, and I apologize for that. The idea was that, okay, I set this equal to 0. I set this equal to 0. This is non-zero. And then I do an equation for sigma xx, which is basically taking the first row, including this, multiplying by the first column, first and only column. So I have, what is it, 1 minus ni times epsilon xx, but because epsilon xx equal to 0, the whole thing is 0, plus ni times epsilon yy also equal to 0, plus ni epsilon zz, which is non-zero, and then everything needs to be multiplied by E1 plus ni 1 minus 2 which is from here. And whether we do sigma xx or sigma yy, we are going to end up with the same equation. Everything else is 0. Obviously, you have zeros here, so you don't care about the shear. But if we assume that x, y, and z are the direction of the axial of the in situ principal stresses, then we don't have shear regardless. So we are lucky. But if we go to the third one, we want to calculate the sigma zz. Sigma zz equals to, we're going to take the third row. So we are going to do ni epsilon xx goes to 0 plus ni epsilon yy goes to 0 plus 1 minus ni epsilon zz, everything times E1 plus ni, 1 minus 2 ni. Okay, and I have now I have two equations, one for sigma xx and sigma yy, and one for sigma zz, which is what I had later on. I want you to be very familiar on how to use this matrix the way I did today and the last time. Okay, so now I know these equations. How about I rearrange to solve for epsilon zz, and then I plug it in here. So I get an epsilon zz in terms of, it's basically something like, let's see, 1 plus ni times 1 minus 2 ni times sigma xx or sigma yy, same thing. Oh, sorry, the microphone, very important piece of equipment. Epsilon E times ni, sorry, not epsilon. And then I plug it in here, and I end up with what I see here. Epsilon, sorry, E. 1 minus ni, 1 plus ni times 1 minus 2 ni times, the microphone will kill us today. 1 plus ni, 1 minus 2 ni, En, and then you have everything here, let's just say times sigma xx. This cancels out with this cancels out with this cancels out with this, and you end up with sigma zz equal to, yeah, sigma xx or sigma yy. Okay, I think this is what's the slide will show. Yes, excellent. Oh, yeah, it's rearranged. Yeah, correct. Okay. Now, remember what we said at the end of module 1, a very important topic that we saw, that was the way the fractures open. And we said that the fractures, mode 1 fractures, open mode cracks, basically tensile fractures, they open by doing work, they open perpendicular in the direction of the least compressive principal stress, right? Which is basically for normal faulting and strike slip faulting stress states, they open across in the direction of SH mean. SH mean is a horizontal stress. So if we have x and y in the horizontal direction, the two horizontal directions, z the vertical, SH mean will be in the XY plane, right? Somewhere there. So if we are looking for the smallest stress, that basically if I'm doing a Likov test, I'm basically trying to open against SH mean, unless I have reverse faulting stress state, which is a different situation. then I will basically use sigma xx or sigma yy as the sigma h mean, which is what I'm opening against. And I can replace sigma zz with sigma v. And therefore, I can have an equation for SH mean, basically, which is what Dr. Benetton derived when he was 29 years old, pretty much. And he did some fitting for data-driven fitting. He would have, if he was today, he would have called it data-driven fitting. But data-driven fitting parameters, he got some data and he adjusted his values accordingly and came up with something that does a good job for the Gulf of Mexico. That was very, very prominent at that time in 1969. Well, it was shallower than what we go on today, but yeah. So you have an equation for basically SH mean just by having SV and the Poisson ratio and the pore pressure. So you only need a value of the pore pressure, a value for the Poisson's ratio, and SV, the overburden, and you can go from that to SH mean. But remember, this is only for when you want to open against, when the fracture gradient, when the fractures are opening against SH mean. If it's reverse faulting stress state, then the SH mean, the fractures won't be opening against SH mean, they will be opening against SV. So if you do a leak-off testing in reverse faulting stress state, you are really getting another indication for SV. So it's confusing. The plane strain theory allows us to approximate a lower bound for the fracture gradient, which is the pressure required to open a tensile hydraulic fracture. Such pressure will be equal or greater than SH mean. So
that's only a normal faulting gradient.
Or strike slip.
Oh yeah, because both are
the smaller S3, yeah. When you do leak-off testing, you don't measure SH mean, you measure S3. It just happens that for normal faulting and reverse faulting, SH mean is S3 is SH mean. Now there are places like in California, diatomite, they were doing a lot of drilling there in the 80s. Diatomite is like kiloliter. It's very, very light. It's where the cats go to, you have for the cats to go in. Or in racetracks, when you have sand traps, those sand traps, not gravel traps. The gravel trap is different, it has gravel. But the sand traps is basically diatomite. It's very easy to make a car that went in fast to stop, but then it's very hard to get the car out of there. And you get stuck there, or if you roll there, you're gonna have a lot of dust coming out. It's very, very light, very, very light. And it's very, very easy to drill through those formations, diatomite formations, diatomaceous earth, as we call it. In that case, because it's light, the overburden is small. It doesn't weigh much. So as V is small, you basically end up with a reverse faulting stress state. And then the fracture will open like a pancake, not like, it won't be vertical. It won't be longitudinal to a vertical well or transverse to a horizontal well. It would be pancake. It would be transverse to a vertical well, longitudinal to a horizontal well. So it's very, very challenging. I know in Vaca Muerta in Argentina, they have areas where it's very, very hard to get, hey Malek, it's very, very hard to get good fractures because of this. So yeah, this is a nice expression for SH mean though, if you have normal or strike slip faulting. And I think you understand how you get the first line. SH mean is sigma H mean plus pore pressure. Then basically you get a value, you replace, basically imagine that this is sigma XX from the previous page, from the previous slide. You replace it with this. And then what is sigma V? Sigma V is SV minus PP.
Sigma Z.
Oh yeah. Yeah. Yeah, it's sigma ZZ. Yeah.
That's what we multiplied from previous slide.
Yeah. So I take the values from the previous slide. I hope I don't have a mistake.
No, it's good. Yeah, it's
Yeah,
correct.
this is sigma ZZ.
I mean, like, because of this slide, you can jump from first slide to second slide.
Yeah. So this basically is sigma V. This is sigma H mean. Okay, I need to erase before I move to the next slide. Okay, so this is sigma XX or sigma YY. This is sigma ZZ. And now sigma ZZ becomes sigma V, sorry, becomes this. And then you just rearrange it, you get this basically. And this is very easy to apply. You just need values, you apply it. And that's one equation you can use for fractional gradient when applicable. We're going to see a lot of equations you can use for fractional gradient in this class and the next class. Because from now, we did advanced drilling, we saw fractional gradient, and we talk about Hamilton-Willis, we talk about Eaton, we talk about, we didn't see it, but I told you there is a Himson and Fairhurst, and there is another guy, I forgot the name. Kelly something. Matthews and Kelly, 1969.
That's for offshore, right?
Yeah. Eaton is also offshore, I think. One of them. And then, but then it was like, okay, that's a fracture. But right now we're getting more advanced. And we're like, okay, it's a fracture, but what kind of fracture? It can be this fracture, it can be this fracture, it can be different. You can have a lot of numbers, and you need to choose the smallest one to be on the safe side. Okay. The gradient is the variation of pressure or stress with depth. Therefore, assuming that the material properties are constant, you basically convert this to basically from a stress to a stress gradient. So I do the derivative with respect to depth, with respect to Z. And if I take Poisson's ratio to be 0.25, I take this, the overburden, the lithostatic gradient, which is delta SV divided by delta Z, to be roughly 1 psi per foot. Then I take the pore pressure to be hydrostatic. I basically get something like 0.62 psi per foot. That's a logical value, but again, don't assume this unless I tell you to assume this. Don't get a question in an exam, what is the fractional gradient, and you say 0.62 psi per foot. You get, I would say only the 1 psi per foot is something that you can assume without me telling you in this class. The rest, I need to give you an indication. So, how do we measure this fractional gradient, or how can we get an indication of the fractional gradient? How does it get affected by the surrounding stresses, the confined stresses. Contrary to fluids, solids does not push sideways with all their weight. Instead, they push sideways with only a fraction of their weight, which is given by the Poisson's ratio that we talked about 2 lectures ago. Proportionally to its tendency to deform sideways. This is basically explaining how it was because a fluid flows and it occupies the entire space that you are putting it in. Now for this, for a solid, if you are in empty space, you push, it can move as much as it wants this way, but it won't flow, Now if you hold it together and you push, you get basically induced stresses on the side because you are having it confined. So unconfined means nothing on the side. I push from the top to the bottom, let's say, and I let it deform as it wishes on the sides. But if I hold it, I put stress like this, then I'm constraining its deformation on the side. So by Newton's third law, basically, if it's trying to push out, but I'm not letting it, I'm basically pushing it inside. Horizontal strains are usually caused by tectonic plate movements. That's what I described, basically. Hence, they are called tectonic strains and say that this is a tectonically active environment, particularly for large compressive horizontal strains that may increase the horizontal stress magnitudes compared to the vertical stress. Basically, when we say tectonically active, think of strike, slip, reverse faulting. Okay, strong horizontal stresses, strong SH max and SH mean compared to SV. Okay, tectonically relaxed is basically normal. What else? Yeah, let me draw. Try to draw what we are talking about here. I have a code retrieved from a certain formation. And I am applying a stress on it along its axis. Let's just call it S axial. No, I would call it SZ. Same thing though. I'm assuming this is the basically Z, X, Y. Okay. Now, I don't have any stress on the side, right? I'm applying only stress on the top of the core, not on the side of the core. So this is any strain that I'm gonna measure confined or unconfined?
Unconfined.
Exactly. It's unconfined because, yeah, exactly, unconfined. Now, what if I have a vessel, special design vessel, and I'm able to have water around the sample? Yeah. And I apply stress all around, not only on the side, like back and forth as well. So I have a stress, I have SXX and SYY.
And both of them are equal.
Yeah, all of them are equal on the side. And then I measure how much SZZ I can apply to get this strain, etc., etc. That would be confined uniaxial strain, right? Very nice. So you need to know the difference between the two. If you do testing, okay, let's just say, what would you think will yield more stiffness, as in Young modulus? Confined or unconfined?
More stiffness.
Yeah.
Confined.
Yeah. If you are trying to see how the rock behaves, a reservoir, Confined or unconfined?
No, confined.
Yeah,
Yeah.
confined.
Because I remember one time we did uniaxial strand, like a different confining to draw
Yeah.
more, more
Yeah.
circle envelope. We're variating a different confining stress.
And the circle was getting bigger and bigger.
Yeah.
Yeah,
So is
yeah.
that stress or strain?
Well, stress causes strain, so the proportionality between the two is Young modulus, right?
But that's not UCS, right?
No, UCS is something else we're gonna see. UCS would be SDZ that you need to break the rock
Yeah, and how about the,
without any.
so this one is SXXSYY or what?
Which one?
The strain here.
The strain would be epsilon XX. Yeah,
Okay.
just like because we have the matrix, remember, and the stiffness matrix,
Yeah.
and we go from one to another very easily. UCS is if I measure what SZZ I need to break it. That would be the UCS, but we are gonna go through it in module 3.
Yeah, I remember. So like increasing the confining pressure was giving like more resistance to the rock to break.
Yeah. I should make the circle bigger.
Yeah.
The circle bigger, yeah. Okay. We saw the 6 moduli of linear elasticity, and we said they are all interconnected one with the other. But there is one modulus that we can make it up ourselves, and it has a physical meaning, but it's not very clear. It's not like Poisson's ratio or Young modulus. It's another modulus that sort of helps make our life easier. It's called the plane strain modulus, E with a prime. Now, if we relax the assumption of the horizontal strains equal to 0 and make them not equal to 0, you have the shear strains. Yeah, the shear strains are 0, but all the normal strains are not equal to 0. Let's just say that they are known quantities. You end up with these equations. And you should know how to end up with these equations from the matrix. Basically, you set sigma XX. So you set this equal to non-zero, this equal to non-zero, and this was already non-zero. And then you end up with these equations. We can simplify it by having basically sigma XX to be equal to sigma YY, and given by this equation for sigma ZZ.
How about the X, Y, and Y? They are 0?
Yeah, they are in the stiffness matrix. There is 0 values, so they multiply by 0. So you don't care about them for now. Basically, you are going to end up with this nice quantity, which is E divided by 1 minus n squared. And sometimes you have it, sometimes this quantity, sometimes you have it multiplied by another one. And yeah, well, here you don't have it, right? But you have it here. Let's see, you have it here, and you have it here, right? E prime.
Is it prime?
Yeah.
And
Look at the title.
Oh, okay.
And then we just make it into, just to make our life simple. It has a physical meaning, but it's very, very, it's a little bit complicated.
we can still make it in the last term. Yeah.
What do you mean?
Yeah, if we divide by E over 1 plus n squared.
Yeah, I mean, we can, well,
1 plus n.
you also have 1 minus b, not 1 minus b squared.
Yeah, so we multiply by 1 plus n.
Oh, okay.
It will be 1 square minus n square, which is 1 minus n.
Probably, yeah. Yeah, so you see how you can simplify it a little
I
bit.
see now it makes your life easy.
Yeah, I did have a paper earlier this year when I looked at scaling factors for using gelatin as a laboratory material to be able to mimic rock. And I used it a lot, actually. It made my calculations a lot easier in the scaling analysis. It always appears for some reason when you have plane strain considerations. Now, a good question is, okay, let's just go back to where we were before, when this epsilon xx and the epsilon yy had to be 0. If you want to model your system computationally, something, make a continuum mass, and you want to model it, you can get close to it, but you're never going to be completely close to epsilon xx equal to 0. So there will always be an error in your simulations with what the equations are giving you. You want to make your model big, big, big. You want to make this hemisphere huge, let's say, but it will never be that huge that it will be epsilon xx and epsilon yy to be equal to 0, right? It needs to be, you need to make it big enough. And that's a lot of, when you write a model for a PhD, let's say, you need to spend time to verify it. We call it V&V, verification and validation. Validation is another thing. Verification is that you need to ask that model a question for which you know the answer so that you build trust in it. So when you ask it a question for which you don't know the answer, you're gonna be confident that what the model is telling you is right. And this is where you play a little bit with what they call the meshing, the grid blocks. Okay, how many, how big are those? Do they need to be, and how? You basically ask it questions for which you know the answer. And it's a whole program. And people are taking years to build those models and then test them. And generally speaking, the more the time they spend in building and perfecting this model, and the more they can use it later. So it's like sometimes it makes a difference. If you spend a little bit more time in making that model good, then you can use it for more stuff. But the time is 3:06. At 3:10, let me know and I will go through the homework. Shall I go through the next slide? We can see the next slide, okay. Reservoir compressibility calculation under linear elasticity. Remember, now in the exam, you don't need to memorize any equations like the matrices and stuff. Those I'm gonna give them to you. But things like how you get from bulk modulus to compressibility, I'm not gonna tell you because you need to know that you reverse bulk modulus, you get compressibility. These are things that you should know. Just like in drilling, I'm not telling them what is how many gallons are in one barrel because they should know. It's some things that it needs to be like they wake you up and you're drunk, you still need to know it. You know, it's like very, very important. Now, how do we calculate the compressibility of a whole reservoir? Okay, remember the reservoir, we have a lot of stuff involved, a lot of phases. Now, focusing on the rock, we said that the rock part behaves like linearly elastic, or is pretty good behaving like linearly, yes?
No.
Oh, yeah, linearly elastic. Starting from the diffusivity equation in one dimension, you really call it, only petroleum engineers call it diffusivity equation. All other engineering disciplines, they call it the heat equation. So I remember I was joking with my classmates when I was young. If they give you a homework in a simulation class or something, and you look into Google and you look for diffusivity, code for diffusivity equation in MATLAB, blah, 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 you won't find much. But if you write heat equation, you're gonna find a lot more, you know? It relates the way pressure varies with time and space, okay? This is one dimension, so we have one dimension in space. Let's just call it X. We don't have Y and Z. It's only one dimensional. You see, it varies how do you call it when it's only on the first power with respect to time and to the second power with respect to space?
Space.
Yeah, my old reservoir simulation professor had a little experiment. He had you take a nail and you light the lighter on one side. It moves basically twice as fast this way than with time. Yeah.
If you will go for rock, it will not move that fast.
No, it won't move that, obviously. Yeah, it's not a,
Conductivity.
it's not a conductor. Yeah. In fact, Arches assumes that they are completely insulator. Arches law. Okay. K is the permeability, mu is the viscosity, and yeah.
So this equation diffusibility, it explains like the pressure, like the PP, how it varies through time while producing.
And space.
And space, yeah.
Yes, sir.
Yeah, because you have time and space means the reservoir location because.
But this is 1D space, so it's only like this.
Okay, and
It could be like this, like this.
That's why you have the viscosity and the permeability as well. Like, yeah, it makes more sense because when the reservoir is like high permeable, it depletes faster.
Yeah.
Then one is less. But the flow rate is gonna be different of production.
Yeah, this is the equation. Actually, when you do reservoir simulation, this is what you are solving.
Yeah, exactly. Yeah.
So you see that this is geomechanics appears here.
That's the compressibility.
Yeah, the total compressibility. Now in a reservoir, you may have water, oil, gas, and rock, right? Each one has its own, each phase has its own compressibility. So you need to add them all together, and basically you do a weighted average. How do you do that weighted average? You take the saturation of each phase, which is unitless, and it's a value that is basically adding up to 1. So basically it's SW plus SO plus SG equals to 1. Okay, if I say this, the saturation of this reservoir is 0.4. It means that 40% of the empty space in the reservoir is basically water. Right? It should add up to 1. So I take the compressibility of each, and I basically do it. It's a weighted average of the compressibility. Now, this is not exactly correct, this equation, but it's good enough for what we do.
Is it like the equation like works for under saturated and saturated reservoir?
Well, if it's undersaturated, you basically have one phase, so you don't have gas.
And
yeah, but that's a different.
you have the permeability.
It will have a different variable here. Yeah, it's a different model. It's a better model than this. But yeah, some people use this. It doesn't always. That's why I said it's a weighted average. It's a good value, but it's not a perfect value. It's good for what we can. If you consider the porosity, it would be, let's see.
You will include the.
Let's just say phi is the porosity. Then you will have
equation.
1 minus phi C rock, sorry. And then you have phi times everything else. CW, SW plus CO, SO plus CG, SG. Yeah.
That's why you're looking for volumes?
It's volumetrically weighted for the rock, basically.
Yeah.
By the way, it would be like this. By the way, in Greek, the phi can be written, lowercase phi is written either like this or like this. Same thing. capital Phi is like this, no uppercase Phi. So anyway, you write it is
Because
correct.
it has to be weighted.
Yeah, this is weighted.
So it's gonna be
yeah.
divided by porosity plus one minus porosity.
Yeah.
Divided by one, basically.
Yeah.
But the bottom one that we have already, it's not weighted.
Yeah, it's I know they use that a lot for some reasons.
For volumetric.
No, it's like you don't you just add I think it has to do with the values. The values that are typically for zero compared to everything else, I think it's much smaller. So it's an approximation, the second one. It's not an excellent approximation, but it's good enough.
Because in the previous one, you're derivating through time and you have your permeability.
Yeah.
So you will know your volumes.
Yeah.
You will have your volumes, while producing, so even the first equation makes sense, the divisibility one.
It's not weighted, it should be divided by two.
Yeah, you will see now why I'm using. Now, if I introduce porosity, we have this, the whole calculation,
Yeah.
which basically relates C-rock to porosity.
Yeah.
So, but this is, and when you see values like these equations with values like this, like weird numbers,
Yeah.
it's a correlation. It's not a,
Empirical.
it's a,
Data, yes.
yeah. The guy ran experiments and he found a certain
And
data.
for this, I guess he ran more than 200 samples.
I didn't read the paper, but probably. So you have a value for hole that you can use that includes porosity to give you C-rock. The value of C-rock would be given by this, as we said before, the change of volume, pore volume divided by pore pressure, and then capturing reservoir boundary conditions in which SV is constant with no changes in the horizontal strains. We call that uniaxial deformation. Boundary conditions is something that you need when you do simulations. You need them both in the reservoirs, in the fluid simulation aspect and the stress deformation, rock mechanics aspect. In this class, we focus on the rock mechanics, like stress and deformation. Those are boundary conditions is what we talk in module one, like SV, SH max, SH min. Those are boundary conditions. Compressibility, it goes both. So it affects both. So reservoir and geomechanics people are interested with that. How does the rock behave against stress? In fact, Hakim read the court documents from the Macondo case, and there was a big conversation in the court about the rock compressibility. What value the BP accident from 2010, because that will determine how much money BP will have to pay as a fine, how much oil went into the water. It's very, very sensitive, the value to the rock compressibility. So there were people on both sides arguing about what kind of compressibility you should use.
So they basically were trying to find a historic matched model that can give the minimum discharged volume in the ocean.
Yeah.
So they can pay less.
Yeah.
And
It's
then the value was very high, right?
yeah. It was they gave the same value as oil. Yeah, which is very weird thing to say that rock behaves the same way as oil. It's very high value.
Yeah.
But it's not the it's very sensitive, the value of Q to
BP, right?
SVP.
BP.
No,
Yeah.
the BP were.
BP was the operator.
Were other third parties who were doing history matching.
No, but BP was in the court. Like,
Yeah.
It was the operator. Yeah.
Capturing reservoir boundary conditions in which SV is constant with no changes in horizontal strains. Yeah. Yeah, uniaxial deformation here basically, it basically says, oh, sorry, that it's something that we are gonna see in the next lecture, to be honest. It's basically if there is no changes in the horizontal strains, like the case that we started the class today, where epsilon xx is 0 and epsilon yy is 0, and only epsilon zz is non-zero, we call that uniaxial deformation. You're only deforming the axis.
Is that possible?
I mean, idealistically,
Like you're pushing and you have nothing coming out?
well, it means that this thing is huge, and whatever comes out like this is very small.
Oh, okay.
It
I thought
doesn't.
it's not considerable.
Yeah, it's negligible. You need to make a model that is that long, like on the grand scheme of things. It's possible. It's good for us, you know. It's like the ideal gas law. It's not ideal for the gas. It's ideal for us.
Yeah, exactly.
Anyway.
No, sometimes it works. The gas stuff.
Yeah, but that's a different, I guess, thing. Okay, in the last minute, I want to go through the homework very quickly. Which was extended to October 4. Sorry, no. Let me open it. And I want to bring it here. Okay. For 35 points, the top of the Bakken Shale is located on average at 10,227 feet TVD. At this average depth, compute the total vertical stress, assuming a lithostatic gradient of 23.8 MPa per kilometer. Easy. Here, total is an important word. Part B, compute the effective vertical stress, assuming hydrostatic pore pressure gradient. You have two keywords here. Effective and hydrostatic. Some people got caught in the first homework. Caught. Caught. Like toggled. Trapped. Yeah. Compute, part C, compute the horizontal effective principal stresses. Horizontal effective is another keyword. Assuming horizontal isotropy, another keyword, or it even explains to you. It's not a keyword because it explains to you what is it. For Poisson's ratio, ni equals 0.23, and the two horizontal strains nearly zero. Nearly zero basically means assume that they are equal to 0. Use the following expressions. It even gives you the equations. So you are finding this. You have calculated this from before, above, and then you know what this is and what. So you basically find, you can find the effective principal stresses, basically. So you get this from part B. I think you know what this is and what this is. And you get the rest. Write the tensor of the effective principal stresses as a matrix. Very easy. Compute total horizontal principal stresses. Again, very easily. Principal is a keyword here. Compute the total. Oh, and total. Total. Don't give me sigma. Give me S. Compute the ratio between the effective principal horizontal stresses and the effective vertical principal stress. So here you want a ratio between effective horizontal, doesn't matter if it is SH max or H max or SH mean, sigma, because effective, and because they're equal to each other. So basically, I want you to calculate this. or they are equal to each other. Compute the ratio between the total horizontal principal stresses and the total vertical principal stress. Now, total is a keyword. I want you to calculate this. SH max over SV or SH mean over SV. Those are equal to each other again. Part H. Compute effective and total, the effective and total stresses, assuming the tectonic strains are epsilon H mean equal to 0 and H max 0.0002. Now we don't have isotropy anymore. Use the same expression as in part C. Okay, very easy. Basically holding you from the hand throughout question 1. Question number 2. You are a young geomechanicist given a cylindrical core from a formation of classified origin and asked to estimate its mechanical properties. The core's length is 3 inches and its diameter is 1.5 inches. That's a weird core, but anyway. You place the core in the loading frame and start applying stress to it and measure a new length of 2.92 inches and a new diameter of 1.513 inches at 2,690 pound force. Assuming horizontal isotropy, measure the cores E and N. Well, it says in the homework if it's confined from the word before. You only applied stress on the top. You didn't apply anything on the side. Yeah, young is a keyword. I would say example problems, number 1 and 2. I think. Yeah. Yeah. Build a spreadsheet in Excel that uses the 2 moduli of linear elasticity to calculate the remainder. For the table on module 2's slide 22 may be useful. See the format displayed on the screenshot below, where you need 15 rows. The moduli on the green and orange UND color cells are used as input to calculate the other 4 on the same row. Submit the spreadsheet separately as a .xlsx file so that your grader, Mr. Kalu, can check if it works as it should work. And basically, you're gonna build this. You're gonna be putting in the green and orange the values, and it's gonna be giving you everything else on the white. And it's gonna be very useful for the future, regardless if you get a career in geomechanics or elsewhere. Question number 4 for 10 points. Use the spreadsheet from question 3 to calculate the remaining 4 moduli of linear elasticity for the core of question 2. What is the core's compressibility? Now, question number 4 has 2 functions. If you get question number 3 right and question number 4 wrong, something is wrong with you. But it can help you verify that your question number 3 is correct. So if you put 2, you need to be getting 4. Then take 4 from here, put them elsewhere, you need to get the other 4. So you can check every row separately and make sure that every row is correct. That's why I have more points in question 3 than question 4. Question 4 is almost like a bonus kind of thing. It tells you how to make sure that your spreadsheet is correct or not. Okay, it's 3:28. I think we need to close.
Yeah.
But
Very nice homework.
yeah, thank you.
You did this year or
Last year as well. Well, this year is a little bit different. We changed some numbers and some questions got like flipped.
But after 10 years, he's not gonna be young geomechanist.
Yeah, it's not the same guy. Yeah, it should be easy. I have office hours tomorrow, 1 to 4. The TA is available. I saw him today, he's fine. He's taking 3 classes, which is crazy. But yeah, we are all available with email or anything. Let us know if you have any questions. But I think it's a straightforward homework. And save this file, this spreadsheet. Don't save it as homework 2, question 3. Save it as something like linearly elastic moduli calculator or something. So something that you can go back to it in the future. You never know where you are gonna get a job. And you know, with metals, for instance, this linear elasticity works much better than the rocks, for instance. So it's applicable universally, linear elasticity. And with that, thank you very much. I will see you all on Wednesday. Thank you. Have a nice rest of your day.